Good afternoon, everybody. Hi, everybody still awake? More or less, okay, good. Let's take this away. I want to talk a bit about trade-offs in data stores. That's kind of the main point, as you will see further on. So I'm Philipp. I work for Elastic, the company behind Elasticsearch, Logstash, Kibana Beats. Maybe you're using some of our products. But I want to talk about, well, trade-offs in general. And, well, my examples will be with our software, but they apply pretty much to anything else. I'm from Vienna. I run various meetups there, and this talk is also a bit about the stuff that I do in my meetups. So I'm running a meetup about databases in general. Well, this will be about databases. And then I also have a group about academic papers, where we basically read one academic paper, the stuff everybody hated at university, we're doing now for fun in our free time. And we're reading an academic paper once a month and then discuss it afterwards. And we do that totally voluntarily. Stuff changes over time, I guess. So, what is the perfect data store in your opinion? There can probably only be one answer. What is the right answer here? Yeah. Who is a consultant? Is anybody a consultant? One or two. What is the answer you're always giving? It depends, right? It's always what you're saying. It depends. And it is really true. As soon as you have a more complex problem, there is no right answer or wrong answer often. It really depends on what you need. And this is what we want to dive in. So basically, the idea is that you need to pick your trade-offs. We'll shortly look at the CAP theorem. Who knows the CAP theorem? OK, that's 1/5 or so of the people. We'll look at the CAP theorem, what trade-offs you have there, and then we also have another idea about trade-offs that I'll spend most of my time at. And generally, the thing you need to keep in mind always is there is no magic. Some people are promising you magic, but actually there is no magic in IT. There is just no way around some stuff. But we'll get to that. So if you have any questions, by the way, if you forget, like me, you can just post them to Slido. So if you go to slide.do, Xera, which is also my Twitter handle, you can just post your questions there. I'll look at that at the end. If we run out of time, I will just tweet out the answers. But you can ask whatever you want, as long as it's within the code of conduct and kind of sane. You can ask anything you want, and I'll try to get back to you, or you come up to me afterwards to ask. And yeah, slide.do/Xera. By the way, did anybody figure out why I'm using that Twitter handle and that name for the Slido question? If we go back a few slides, it has something to do with my name. I know it's kind of late. Anybody can guess what it has to do with my name? Anybody remembers good old Rod 13? Where you would rotate the letters by 13, like you go from A to B to C, etc., 13 times. And when you take my last name and do a Rod 13, that is what you get out. The nice thing about the Rod 13 is if you do it again, you're back at the original, because, well, 13 plus 13 is 26. That's how many letters there are in the alphabet. That's why that was very common. Anyway, that's just as a side explanation why this weird name. OK, so CAP theorem. Let's see what the CAP theorem is about. So there was this paper about the CAP theorem, or there is this paper about the CAP theorem, which states that Brewer's conjecture and feasibility of consistent, available, partition-tolerant web services. It's not just about web services, it's really about any distributed system that you have. And the general idea is you have these 3 attributes, but you can only have 2 of them at most if you build a proper system. If you build a bad system, by the way, you might have only 1 or 0 of these attributes. So it's not kind of a given that you will have these attributes. So the first thing that you normally want to have is consistency, which basically means you have a total order of operations. Let's assume you have a distributed system with multiple nodes. What the consistency here means basically that the data looks in the end as if there was only a single machine and you were sending like 1 request at a time and it was processing like everything in the same order. So you guarantee the total order over the entire distributed system. So it looks like there's only like basically 1 queue with 1 lane and everything is passing in the same order through that for the entire system, and that's what you get. So that's the consistency. Then you have availability. Availability is generally the idea as long as a node is reachable over the network, it should respond to your requests. So a node cannot just say like, I'm not sure what kind of data I have, I will just not answer this one. Then you're not available. Basically, that's the condition of availability. As soon as the node is, or as long as the node is reachable, it should answer your queries. And then you have partition tolerance, which is it can lose arbitrary messages. That's kind of in a distributed system. Well, there are these fallacies of a distributed system, like all the things that can go wrong. And that's pretty much this point that, well, stuff can get lost or delayed or is just out of order. So you need to live with that and need to compensate for that. And generally what you have these 3 attributes, but you can only pick 2 at most. And you can see you can have either a system that is CA, AP, or CP, but there is nothing in the middle. There is no way to get into the middle. And actually, to prove that, it's pretty simple. Also, the paper is very simple. It doesn't have any fancy math proofs. It's very constructivistic. So what it's doing, basically, it's saying, like, let's assume we have 3 nodes, and the network is breaking in the middle, and we have 2 nodes on one side and 1 node on the other side. So you have this network partition. And then you do a write operation. Let's say you do your write operation here. And then this other node on the other side then will have to decide, like, am I available? So I keep answering queries, but I know that I cannot see the other nodes, so I might give you outdated answers. Or am I consistent? Then I see, like, oh, I don't see the others. Maybe they have other data than I have, so I will stop responding. And that's the basic trade-off that you need to make. Are you consistent? Like, okay, you might stop responding because you know you might not be consistent with the rest of the world. Or are you available? You keep answering, but you might serve outdated or wrong information. That's the entire idea. There are some misconceptions around it. One of the misconceptions is that fault tolerance or the network partition is a choice that you can make. Some people claim that, oh, our network is so good, we won't have network partitions. It's just not happening. Normally what is the case is maybe your monitoring is not good enough and you just don't see them. Or you have been extremely lucky, but they will hit you at some point. So you cannot really just say, like, oh, network partitions are not a thing. You need to make the choice up front. And if you don't make the choice explicitly yourself, something will happen and you don't really know what it will be. So if you don't make the choice up front yourself, the system will just behave like unexpectedly. And that's probably worse than if you make that choice. The second thing is sometimes people confuse the consistency of ACID, the atomic consistent isolation durability, with the CAP theorem. Because both are consistency, but they're different kinds of consistency. What you have in ACID is consistency in you have a correct state, so you have referential integrity, or you have a column that is an integer, and every value is still an integer there. And if you do an increment, it will just increment to the next value. Whereas the consistency in the CAP theorem is about temporal consistency. So basically, at one point in time, you have one consistent view over the entire distributed system. And it doesn't matter which node you basically ask for an answer, they will always give you the same answer at one point in time. That's the temporal consistency. Whereas the ACID consistency is more like a predicate, like you move from consistent state to consistent state. That's the idea there. And then if you want to explain that to your kids at home or to your parents, what is the CAP theorem? You can do it with Robinson Crusoe. Because Robinson Crusoe, I think he was English, and he was on his lone island. So basically, he was partitioned from the rest of the world. So you have the network partition again. And let's assume a ship comes by and asks him a current question. For example, who is the king or queen of England at the moment? And then Robinson Crusoe has to decide, am I consistent or am I available? Because he can either answer, and then he's available, but he might not be consistent with the rest of the world. Or he might say, like, I don't know, but then he's not available because then he's not answering the question. And that's the general idea of the CAP theorem, and there is no good way around it. By the way, you have these eventual consistent systems. That's pretty much like the message in a bottle, that every now and then there is a newspaper in a bottle or so being swamped upon the island, and then he reads who was the king like 3 months ago. Like our modern distributed systems probably don't have like a 3-month eventual consistency, but it's more like milliseconds or seconds. But there might be this eventual consistency where not the state is guaranteed at one point in time, but it might be slightly delayed. Yeah, did you recognize the island here? It's from Star Wars, and I'll do all my examples on Star Wars here. So yeah, this is one of the Star Wars islands already. You can break CAP, but you won't get sensible systems out of that. For example, def null is breaking the cap theorem. Because, well, you can always write into it, and you will also always get the same answer out of it, nothing. So that's one way how you could break the cap theorem, but it's not a useful system. There are people who try or claim that they broke the cap theorem, but in the end, there's always like some workaround, or you have a system that is not really usable in the end anymore. So saying you break the cap theorem is not really a feature that you can claim. And it's just a very basic thing that is very hard to break. Okay, so that was the cap theorem. And we at Elastic, one of our colleagues, has made up this so-called fab theory. Here's Mark. You see him at his favorite hobby, he's skating. Normally, unless he injures himself again when skating, that happens every now and then as well, unfortunately. But that's what he's doing. So Mark, he has this fab theory. And the fab theory is you have 3 attributes again, and again, you can only pick 2. So you have fast, accurate, and big. Fast is pretty much like you have a real-time system. It's not a batch. Real-time, I would say it's like everything you would make a user wait for the answer, and you don't go for a coffee or a smoke break or anything. So you basically make users wait for the answer because it's coming back within a second or so. That's probably what users expect. So that's fast. Then you have accurate. Accurate is kind of, that is what you expect from your data. It's the exact result that you should be getting. It doesn't have a rounding error. It doesn't have any error of margin of error. It is the exact value. And then you have big. So big is just, I would say you scale it out horizontally. So you go beyond one machine. That's stick too big for that. And I don't like the term big data. While everybody's throwing around big data, let's forget big data for today and just say like we need horizontal scaling, and that is what we call big. Okay, so fast, I guess, is clear, like you wait for the answer. Big, you scale it horizontally over multiple machines, is also kind of clear. But what is kind of the trade-off around exact? Like normally you would always expect your results to be exact, right? Who would want to get a wrong answer, basically? Let's see what is the trade-off, or what are the trade-offs around exactness that you can have. Well, I'll use my Elasticsearch examples, but it applies to other systems as well. The one thing you need to know is to scale Elasticsearch, we call something a shard. And the shard is basically you have an index at a thing where you put related documents into, and then you can break that into one or more shards. And one node can hold one or more shards. So for example, in our example, we'll start off by having 5 shards, and then you could distribute those 5 shards over 5 servers. So every server keeps 1/5 or one chunk of the data. By the way, does anybody know where the term shard is coming from? Because shard is kind of a common term for breaking things up and distributing them. But where's the term sharding actually coming from? Anybody remembers this one? Who was playing a lot of games, like some time ago? So here you can see in Ultima Online, that is one theory. I'm not sure if it's really true, but that's the theory that I've read, and that's kind of the oldest one I could find, is that they have this thing where there is the evil wizard and he traps the essence of the world in a crystal, and then the crystal is shattered, and then you have the shards of the crystal, and each one holds a part of the copy of the entire world. And that's where the sharding concept is coming from. So you have this shattered crystal, and that's how stuff is broken up. That's why a lot of systems call these broken up things shards. But again, that's just a side quest. So the first thing is you want to have a term segregation. Term segregation would mean like how many times does a specific term appear in my data. So let's say we're sticking to Star Wars. This is the very first Star Wars movie. I'm never sure which number that is now because numbers got very confusing in the Star Wars ecosystem. But that's the oldest movie. And here, somebody, luckily it wasn't me, counted like how many times specific terms appeared in the Star Wars movie. And you can see Luke appeared 64 times, R2 31, Alderaan 20, etc., etc. So we have these, I think those are 16 terms, and we have how many times they appeared. So what I've done is basically I have created an index I call Star Wars. It has 5 shards. And then I insert my document. So basically, I have inserted Luke 64 times. And then I have R2, which was, what was it, 31 or whatever. And I have 31 documents with R2. So I store that information. And then I want to query how many times do my documents appear here? And you could also visualize that just to give you a quick idea how that works. Let me quickly switch my setup here. No. Stay where you are. No, I just plugged it back in. It's all good. So you can see here we have Luke. I'm just searching for Luke. It appears 64 times. By the way, well, what would be the SQL equivalent of this query here?
Count.
Yes, it's a count, though actually you can see I have the actual documents down here. So it's a combination of a count, but also like it's a select where name equals, where word equals Luke from Star Wars, something like that. So it's a very general query. And you could draw that out. So for example, you could say here, I want to visualize something. And you could just say, I want to create a new visualization. The one I'm interested in is a tag cloud, for example. I pick my Star Wars index where I put all my data in. And then I say, yes, I have a tag. And I want to say, give me on a specific term. The term I have is the word, which we have here. And then you could say, for example, I want to visualize my top 20 terms. And if you run that, it will tell you, okay, Luke is the largest one, so this is appearing most times. So you could easily visualize that. And this is also running an aggregation in the background. But let's look at the raw aggregation as a query as well and what the result of that is. So for example, here, this is the raw query that I'm running. So you see, this is an aggregation. I call it most common. And basically what I take is I take a field, the word.keyword, and I want to get the top one hit there. So I aggregate all the terms together, and then I want to get the most common term out of that. And if I run that, how many hits are you expecting? 64. Okay, we run that, and it says Luke appears 56 times, which is kind of wrong, right? And you might be very confused and say, like, how can this even happen? So you've seen those queries, and then you basically know it's not true. That's impossible. And now we'll look at why this is actually happening. So I've cheated a bit here. I've skewed my data and made it unevenly distributed to get that effect. Normally this probably wouldn't happen, or at least not that strongly. But what I've done here is we have the concept of a so-called routing key. The routing key basically tells Elasticsearch where to store a document on which shard. And what I've done here is I've taken the routing key, and the first 10 documents have the routing keys 0, 1, 2, 3, etc., until 8, 9. But afterwards, all the 54 other documents have the same routing key, so 0. And how we determine where one document goes in Elasticsearch is basically what we do is we take the routing key, we hash it, and then we count it modulo the number of primary shards. So if you take the routing key 0, you hash it, that will always be the same, and then you count it modulo the number of primary shards, that those documents will always end up on the same shard. How many primary keys did we have? 5, which is also the default in Elasticsearch. Why are we hashing the routing key? Sorry? Yeah, so the idea of why are we hashing is to have it evenly distributed. For example, let's assume you have usernames, and then you might have the usernames people pick, they're unique, so they might be a good key to distribute that, but the usernames are maybe not evenly distributed amongst the entire key space. So I'm not sure what is the most common letter in Spanish, but for example, in English, the most common letter is E. So probably you have a lot of people have the starting letter E, and then whatever Q or Z or whatever is the least common one. So you might have like a hotspot and more people around E than around others. Whereas if you hash it, then your key space is very evenly distributed, and all the shards will get an approximately even number of documents. Though, since I have taken this routing key 0 here, the data is not evenly distributed, and I have a lot of looks on the whatever 0 hashed and divided by the modulo is. So I have a lot of looks in one shard and very few looks in the other shards, but that's intentional. And if you look at the data, basically you can look into the shards where the documents are. So basically for the first keyword, that always, or most of them go to the shard 0, or the routing key 0. And then the second term mostly goes to the shard or the routing key 1, etc. So you can see the documents are not very evenly distributed. You can see here, these are the primary shards, 0, 1, 2, 3, 4. The 5 primary shards, and here you can see how many documents do we have in each one of them. So you can see, for example, 2 and 0 have a lot of documents, whereas, for example, 4 only has 26 documents. So your data is not very evenly distributed. And we're basically making use of that in our example here to show why the calculation is wrong. Normally, if you have a generated ID, your routing key or the IDs would be evenly distributed, so you would not really have that problem, but I wanted to illustrate the problem. That's why it looks like this here. So what we do is basically, since it's a distributed system and we have these 5 shards, every shard counts their own top terms. And what you do is you take, every shard doesn't count all the terms, but it makes an optimization. It just counts its top n, and this is the formula here now for the top n terms that it is counting. So here you say you have a size. How many results do you want to get back? What size did we use in our example query? 1. We only wanted the top 1 document. You multiply it by 1.5 and then you add 10, which comes down to how many documents in our example per shard? 1 times 1.5 plus 10 is... Yes, it needs to be an integer because it cannot send half results. So 11 or 12? Any guesses? It will be rounded down. So you will get 11. So basically every shard will send its own top 11 terms and it will count them correctly. But if you have more than 11 terms, like we do, we have 16, then some results will not be sent. And that's basically where that error is coming from, that we're not sending some of these results. So generally we have 11 results per shard. How many results do we need to combine in total? 55, right? We have 5 shards. Every shard is sending 11 sub-results, and then we combine those to the total result. That's one optimization why this is much faster. For example, let's assume you have a proper use case where you don't have 16 terms, but you have a few thousand terms. And then you would need to count those thousands of terms, and then every single shard would need to send those thousands of terms, and then one node would need to combine all those sub-results into the final result. And that might be too much to keep in memory and blow up the heap. And that's why we do this optimization, that we only send a sub-result. And that's kind of an approximation why this might often be good enough, but it's not always good enough. You also have, if you look here, if we move down a bit here, we can say, I want to see the error count. You already see here there is an error count. So basically this one says here, some of other documents, basically there were a number of documents that are not part of this result because maybe they were not loops, or because there was an error. And also it tells us overall the error count is this result here might be off by up to 10 on a global level. So even if you calculate the top 10, the document error upper bound would apply to each one of them. You could also slightly change the query to this one here, where you basically say, I want to see the error count on a per result level. So you can see on a global level we have up to 10, but on this specific one we only might be missing up to 9 results, which is still slightly too much because we have 64 and well that would be 65. Any ideas how we might calculate that error bound? Basically, if we send 11 results, we know how many times does the 11th position appear, like let's assume 3 times, but the 12th element might also appear 3 times. So basically then we add 3 to the error count and say like, well, there could be 3 more that we didn't count in this one. That's how we get to that error bound. Okay, and now let's change the shard size. The shard size is basically how many results does each shard send back. 11 would be the default that is kind of like built by that formula, but I'm setting that to 20. If I set it to 20, will my result be correct in the end, yes or no? Yes, because we only have 16 terms. If everything is sending its own top 20 results, well, it will only send 16 because it only has 16. So this will actually be correct. And this one, you see here, the error bounds are now 0, and you can also see the result here is 65. But, well, you need to do more calculations. By the way, let's assume you would set the size to 5, so you want to have the top 5 results, and you only set the shard size to 2. Any guesses what would happen then? It doesn't make much sense if you want to calculate the top 5 results, but every shard is only sending its top 2. That would be totally off. That would automatically set the shard size needs to be at least as large as the size. So if you have 5 here, this one would be automatically be set to at least 5 as well. Or if you set a higher value, that higher value would be used. Or if you don't set a value, it will use the formula where it's multiplying by 1.5 plus 10. So if you set that to 5 here, what would be our shard size? $12, hopefully. Oh, sorry, no, I cannot calculate. So it's 5.1.5 is 7.5, rounded down to 7, plus 10 is 17. If you do the right calculation, that's what you should get. Okay, so that's this part. We've seen those. It's just there for completeness sake. Okay, cardinality aggregation. Basically, the cardinality aggregation, you want to know how many unique terms are in my data set, which might also be very expensive. If you have a large data set, counting how many unique terms are there might be expensive. How might you calculate how many unique terms are in a specific field? What would be the naive approach? You might just use a hash set, where you have like, you put every entry in and then you count all those entries in the end in the hash set. However, that is not very predictable in storage and performance size, because if you have a very large size, again, it would grow linearly with the amount of data that you have, which you probably don't want to do. There is a very fancy paper again to show or make that work better, which is called HyperLogLog in practice, and then there was an optimization, and now it's called HyperLogLog++, which is kind of a long name, but that's how it's being called. So what you generally do is you have a binary representation of your values, and then you count the leading zeros. And the assumption is the more leading zeros you have over all your data set, like you take the value with the most leading zeros, the longer that those leading zeros are, the more unique values you have, because by pure random distribution, the more leading zeros you have, the more results will there be. So this is just basically using this trick, and it's hashing that so that the jump is not too large if it has like randomly 1 or 0 more or less. Well, that is how we calculate that. So we take that bit value of how many leading zeros we have, n minus 1, and then we multiply 2 to the power of that n, and that is how many unique values we assume we have. To skew that out a bit, there is some stochastic averaging to get kind of a more even distribution, but that's getting pretty deep into statistics, to do that calculation. So let's see how that calculation works. What you want to do here is, I'm using an external mouse that is kind of super weird. What I want to do here is I want to do that cardinality aggregation. And I want to have how many unique words do we have. And right now I set a precision of 16. The precision is basically up until this precision value, the count will be correct. If it's higher, there might be some fuzziness. So if we run that, what should be the correct result here? How many unique terms did we have? 16, exactly. If I run that, now it assumes, well, we have 17. So it's off by 1. If you increase that precision threshold, if you just go up to 12, then it's already correct. What are the trade-offs here? Let's see, if you will get the slides afterwards so you can try out all the queries. So the precision threshold by default would be 3,000 and the maximum of 40,000. If you try to set a higher value than 40,000, we will automatically set it back to 40,000. There is no way to go larger than that. Why? Because it has a memory implication. Basically, you take the precision threshold, multiply it by 8 bytes, and that's how much memory you will need for that calculation. And well, you can do the calculation and know how many unique terms you try to calculate, how much memory you're actually using for that. So here we have tried it out with various thresholds, 1,000, 100, and 10,000, what the relative error is. And you can see if you use 100, okay, the error might go up to 5% or so. But as soon as you are using 1,000 or 10,000, your errors will be like 1 or 2% at worst. So that's how much error margin there is in the unique terms. And oftentimes this is good enough. But again, you could set a higher threshold and then you would get more exact results by trading for more memory. Yeah, we've seen that. That is giving you the correct result. Sometimes people ask, like, maybe we should pre-compute those hashes. Does it make sense to calculate the hash for the leading zeros? Who thinks that it makes sense to calculate those? Who thinks it doesn't make sense to calculate those? What is the right answer? It depends, of course. That's kind of the takeaway here. You're getting it. So in some cases, you want to have that. For example, if you have a large data set and a high cardinality, it might make sense to pre-compute those hashes to see the leading zeros. Or you have the low cardinality, or a numeric field, because those calculations on numeric fields are very fast because CPUs are very optimized for that. You don't probably want to do that calculation. A, because it's taking more time when you store the results because you need to hash it then, and B, because it takes additional disk space to store the hash. So in some cases it might help, in other cases it probably doesn't help. There are improvements. People tried to improve HyperLogLog++. There was one that is called LogLog Beta. We tried that. We actually had a pull request ready to be merged, but it turned out to not be an improvement overall. So then we never merged the pull request and just threw it out. There is another new paper which is called HyperLogLog Sketches. We have not implemented that yet. We have an open issue, I think, or somebody thought about trying that one out. Maybe that one will give you better precision for better memory use, or at least one of them will improve. But, well, we need to implement that and then see if it's actually true. But right now it's still this HyperLogLog approach, HyperLogLog++. You hash, you count the leading zeros, and that's how many unique values you basically assume you have. Then we have another very interesting one. So let's assume we search for Luke. And this is now a full text search problem. If you search for Luke, here we're searching for Luke, and basically you search for Luke and you find a document and it has this relevancy here, the score. This is basically how well does my query or does this document match my query. And you can see here, I'm searching for Luke, my entire document consists of Luke, and you have a score of 3.2. But if you scroll down, like in total we should have 64 results here. If you scroll down, you will see that suddenly the Lukes change, because this one suddenly only has a score of 2.9. And if you go further down, it's only 0.2. Why are the scores so different? Wouldn't you expect the scores to be the same for all the queries? Because, well, it's the same query, it's the same documents. Why are the scores, why is the relevancy so different between some documents versus other documents? Any guesses? So it depends on how, or the thing is, how do we calculate the relevancy? Let's see how that relevancy is actually being calculated. So how to calculate relevancy is we have something called TF-IDF, term frequency inverse document frequency. And there are three main components. And one of them is skewed here again because the documents are not evenly distributed. Actually, the actual algorithm that we have right now is called BM25, which stands for Best Match 25. It's the 25th iteration of the best match algorithm. Maybe we'll have a BM30 at some point in the future, but right now it's the 25th iteration, and that's kind of like the golden standard for now for full text search. So what you have is generally the term frequency is how many times does a search term appear. Since all of our documents contain Luke once, that's the same for everything. But for example, if you had a longer document and Luke appeared in one document 3 times and in another document once, the document containing Luke 3 times is kind of more relevant for the Luke search than if you only have it once. Hopefully kind of intuitive. it looks something like this. So basically here you have on the x-axis, you see how many times does Luke appear, for example, or whatever term you have. And then on the y-axis, you have the relevancy. So let's assume Luke appears once, then it's kind of mildly relevant, whereas if it appears 5 times, it's more relevant. And then you see TF-IDF assumed, well, if it's appearing 20 times, it's still more important than 15 times. And BM25 kind of capped that off and said, like, well, once it appears 5 times, there's not much difference anymore. That's the term frequency, but that's the same everywhere. Where our difference here comes from is the inverse document frequency. The inverse document frequency basically says if you have a term that appears very often or commonly, it's not very valuable because it's very common. Whereas if something is rare, then it's very valuable and the score should be higher. And it looks something like this. What you do here basically is the x-axis is how many times does your term appear. Like if it's 10 times, it's much more relevant than if it's hundreds of times. And you can see it's basically falling down. So that's the general thing. The problem is, by default, we are only calculating that on a per shard level. That's why our results are so way off. I'll show you in a moment how we actually do that. And the final thing, by the way, to calculate the score is the field length norm, where we basically say how many terms are in your field. And we have that 1 divided by the square root of the number of terms, which is kind of intuitive if you have a very large field. And if your search term appears there, it's not as relevant if it's a very short field. So if it's a short field, it might be like a title, and a long field, the full text body. So if it's in a short field, your term might be more relevant. So how do we actually get documents if we search in a distributed system? What we do is it's called query then fetch, and it looks something like this. Here you can see we have, let's assume we have 3 nodes, and you see we only have we only have 2 shards. You see we have primary shards and we have replica shards. Forget about the replica shards for now. What we generally do is our 2 shards here, we want to search. And basically your client or your application or whatever is sending a request to your cluster to answer the query. And it will round robin between all the nodes in the cluster normally. So it will hit one of those nodes. And that node in our example is node 3. And we assume, or we call node 3 the coordinating node. So it's you coordinating your request. And it's basically your request, your search for Luke is hitting the coordinating node, node 3. And that one then figures out, okay, you're querying the Star Wars index. The Star Wars index, in this example, only has 2 shards, to keep it simple. And it will then go to one of the shards, or it forwards the request to each one of these shards, because it might not be on the same node. Here you can see it's sending the request to the 0 shard, to that replica, and the primary shard there. So it's sending the request to each one of those shards. And then each shard is basically calculating the score for all the relevant documents, for all the Lukes. And then it's forwarding that score to the coordinating node again. So by default, we would search for the top 10 terms. So how many terms does each shard need to give back then? Basically, if you search for 10 terms, every single shard would need to hand you back the list of its own 10 documents. Or for example, if you only search for 1, then every shard would give you its own top 1 result. Because overall, you don't know on a global level which ones are the best 1 or 10 documents that you have. And then you have the fetch phase. In the fetch phase, the coordinating node got the list of the top n documents each node has, or each shard has. And then it's saying basically overall, the top n documents that I need to fetch are the list of those. Because every shard is only sending by default back the ID of the document and the score. And then the coordinating node will figure out overall the top 10 documents are these. And then it's using the ID to actually fetch from those shards the overall top 10 documents. That's basically the coordinating node is then sending out a multi-get to get the right documents from both shards. And those would then reply with their documents, and then the coordinating node would hand back the total result to your client again. That's how we spread out searches in Elasticsearch generally. The thing is, IDF, how many times does a term appear over all the documents, is only calculated on a per shard level. We don't have a global statistic. You could do that by adding a thing called DFS query then fetch, and DFS stands for distributed frequency search. Where you basically add a parameter to your query, and then instead of having like 2 like rounds where the coordinating node says like, give me your best, the IDs of the best documents, and then it fetches the documents. You would add a step before where the coordinating node would basically say like, give me your statistics for that term. Then you calculate the global statistics. How many times does loop, for example, appear over all the shards? And then with that, it would calculate the top 10 results for each shard. And then the statistics would be the same for every single shard. You can try that out here. If you run the query then fetch query, you could then see here, this one has 1.5 now because the statistics have been evened out. And even the last one here still has 1.5 as a score because we have evened out those statistics. So the assumption is, or what do you think? Should you always use DFS? So this is the right result. So that's kind of easy. You just add DFS and then you're done, right? Yes, no, maybe. Well, generally people then ask like, okay, when we do DFS, how much performance overhead does it cost? And that's one of my favorite comics for every performance-related question is, how does this really behave, especially if you try to benchmark something against another system? It's normally you find one scenario that works very well for the one thing that you want to have win in that case, and you make the other system kind of suffer or the other approach suffer. We don't really know. So what you generally, if you add DFS to your queries, you will definitely have one network round trip more. So the coordinating node needs to do one more round trip to all the shards. Also, they need to get the statistics, the inverse document frequency from every single shard. Depending on if that is in memory or only on disk, it might take a little longer. But there is definitely an overhead. And generally, our documentation is, so it has this relevance is broken. That's where our documentation explains why the scores might be so different. But that page also describes why you should not use that in production. And it's pretty explicit, it really isn't required. Why? Because normally when you have a reasonable amount of documents and you don't have a stupid routing key like I did, your documents should be pretty evenly spread out over all your shards. And then you don't have that problem. So normally, if you have like either incrementing IDs, and those would be hashed and evenly distributed, or if you let Elasticsearch generate the ID for you, those should also be very evenly distributed. And if you have enough documents, those would just happen to more or less evenly spread out in your cluster, and then you don't really need DFS. Only if you use a bad routing key, then you might need DFS. What might be one scenario why you might, or let's ask it differently. Sometimes you might want to have locality, where you say you want to have related documents on the same shard, so you can get more results from that from one shard together. What might be one scenario where you could be doing something like that? So for example, I know some shops have they have seasonal offers, and they might try to put most seasonal offers together. And then you might have the case that, oh, the new iPhone comes out, and then suddenly you have much more offers for iPhones because, well, it's a new thing and everybody starts to buy the new iPhones. And then you might have an uneven distribution. When you try to split up your data, for example, by date, and then you have an event, and then you might have more events on a specific day about iPhones. For example, if you have a news site, and like iPhone news is like, not much is happening, but then there is a new release, and then you have lots of press releases about iPhones. And then your data might not be evenly distributed. Then you might have scenarios where DFS could come in handy, but normally it's really not required. And to counter that general problem, in the next major version that will come out, we will change the default number of shards, and it will just be 1, because, well, the number of shards have been causing too many troubles. Also performance-wise, because, well, people have been using too many shards. By the way, does anybody know how many shards should you have in an index? What might be an indicator how many shards you should have in your index in general? Yeah, it depends, but we have the rough idea we would normally say is one shard should be quite a few gigabytes. Normally we would say, depending a bit on the use case as well, one shard should be 10 to 50 gigabytes of data. So if you have shards in the megabyte range, it's not a good idea because there is some overhead to the shards. Also because if you have very little data, then again, you might have unevenly distributed data and you just have unnecessary trouble. So don't do that. And that's one of the reasons why we changed to a single shard. And Simon, who is our tech lead, he always says, like, how do you figure out how many shards you should have in your system? You start with a single shard. You see when it blows up. And then you calculate how many times that much data do I have. And that's the number of shards you need, or maybe you need leave 1 or 2 spares. But you basically start with one shard, fill it with data, and when that shard blows up, that is the maximum of how large one shard can be for your use case. And then you calculate for the overall data size that you have, that's the number of shards you want to use. So let's actually change it a bit. So I'm blocking the write operations to my Star Wars index, and I will create a new index. And this one is not called Star Wars, but I will call that one Starlet, like the little brother of Starlet Wars. And I will basically take the Star Wars index and shrink it down to one shard here. So we're taking the Star Wars index and put it into the Starlet Wars index with a single shard. So everything should be in a single shard now. And then the question is, will my queries work better? So if I run the general query for Luke, will my scores be correct now without DFS? Yes. That one will work out because you can see it's 1.5 and you can see it's always 1.5 because, well, the IDF part is the same because it's only one shard. There is no point in doing, there is no point in DFS. If I calculate the most common terms and so here I want to get the one term, will that calculation be correct? Yes, because, well, every shard is giving me its n top results, but since there's only one shard, there is no bad combination that could happen here. So if you run that, you can see here we have Luke with 64 documents, and there's an error bound of 0, because, well, one shard, there cannot be any error in combining missing or because of missing sub-results. That's what you get here. What happens if you run the query with the precision threshold with the cardinality? Will that be exact or will that not be exact? Well, that is the only one that is still counting wrong, because there we are just calculating the leading zeros. There the number of shards doesn't really make a difference. But the other ones, there you have this difference. So we have seen those. So the cardinality count, that one doesn't change. But you might say that was kind of a cheap trick, because in the fab theory, what have we done now? We've kind of changed the trade-offs, right? Because we used to have fast and big, but now with one shard, we basically have fast and accurate. We don't have big anymore because we cannot spread it out over multiple nodes anymore. One shard can only be on one node, so it's basically giving up that big attribute in our system. And that's kind of the trade-off that we've taken here. So you can make it totally except for the cardinality aggregation, but the other ones are then correct, but it's not big and able to spread out over multiple nodes anymore. So to wrap up, it's kind of always about the trade-offs that you have in your system. And Elasticsearch, but also any other data store has these trade-offs, and you need just to be aware of what the trade-offs are to actually make use of them, to either get faster results or use less memory to do some calculations, or be able to scale out more. Well, we have covered the CAP theorem, consistency, availability, and partition tolerance, and fab. We don't have an academic paper for that. Or at least not yet. We don't have like any fancy background to prove it. For us, it's only a theory. So we have this fab theory, but I hope that intuitively it kind of makes sense that there might be a point to that fab theory. And with that, any questions like you want to have right now? And by the way, before you run off, I normally try to take a picture with you so I can prove that I've been working today. Because my boss doesn't know where I am. Regular photo. Everybody smile. Wave, yeah, wave. Thank you. Very good. Any questions? Do we have a microphone for questions? Thank you. Any questions here? Otherwise, we can also head over to Slido and see, did anybody ask any questions on Slido? No. Nobody dare to ask any questions? No? Any questions now? Final chance? Okay, if you don't have any questions, enjoy the rest of the afternoon. We have a couple of stickers over there. If you want to grab stickers, grab some stickers. If you have any Elasticsearch questions or anything, come to me afterwards, and I'm happy to help you out with that. Thanks a lot.